In this video, we'll introduce rolling motion. So you take some round object and you roll it on the ground. It will have rotational motion, so it'll be spinning like this, but it'll also be translating, so it has some velocity, translational velocity as well. In this class, we won't deal with any slipping, any rolling with slipping, and that just means when something's slipping, there is relative motion between the two surfaces, like um, the object here in the ground. An example is like peeling out. If your tire is spinning like this and there's relative motion between the ground and the tire, that's slipping. I was thinking of like a bowling ball the other day where, yeah, so I rolled the bowling ball. I was bowling the other day, and for a moment, this thing was actually not rotating. It just had velocity v. Okay, it was going like that. And so there is relative motion between those two surfaces because the bowling ball just kind of skidded along that way. So it was slipping, but so we won't deal with any of that here. It's just something that's rolling here and the two surfaces in contact, there's no relative motion there. If we look at an object that's a round object that's only translating, could be a wheel, and it let's say we're moving it with velocity v. And we looked at 3 points on this wheel. We can look at um, the the axle here, the where you would have like an axis of rotation, the top of the wheel and the bottom of the wheel. Now, if I'm just walking with this thing and it's not rotating, then each point has velocity v. Right? You take a wheel, like a bike wheel. Let's say you're taking it, just walking with it. You're walking some v here, and it's not spinning, it's not rotating. Then each point moves forward with the same velocity v. Now consider the same wheel, but this time it's rotating only, so it's not translating, it's just rotating. Well, the axis of rotation has zero velocity, stays in place. The top of the wheel, if it's going in this direction, whoops, it's going in that direction, has velocity v. And if it's spinning this way, then the bottom of the wheel has velocity, but in this direction, velocity v. Now, what if that wheel is both translating and rotating? And we can think of a wheel, your car tire or something like that. So not only is it rolling this way, but it's also moving in that direction. What is happening at each of these 3 points of the wheel? The bottom, the axis of rotation here, and the top of the wheel. Well, earlier I said that we're not considering any slipping. And so when the wheel comes into contact with the ground, sure enough, this has to be zero velocity down here. And I'll show you in a second here how that kind of makes sense. The axis of rotation here is moving forward with velocity v, and the top of the wheel moves forward with velocity 2v. And I'll kind of show you one way of looking at this. If it's translating and rotating, what you can do is add up the velocities at these points together. This would be like in the positive direction. Yeah, we could say it's like positive. This would be negative, and so v minus v would be 0. We would add v plus 0 here would just be v, and v plus v is 2v. Now, this makes a lot of sense. If you're driving a car, the axis of rotation here, like the axle of your car, is moving with the same speed as the car. Okay, we said that the bottom of the wheel is not slipping against the ground, so there should be zero speed relative to the ground there. And at the top of the wheel, this actually is kind of interesting. As this wheel is spinning, imagine a point here on the back of the wheel, and your car is moving forward with velocity v. Well, at some point in the very near future, this point will go in front of the axis of rotation here. It'll be here and then it'll be here. So at some point it had to be faster than v, right? And so at this point here, it is going to v, right? In order to get in front of this, it traveled faster than that. Okay. For today, um, for rolling, when we talk about speed or acceleration, we'll take this equation that we have, and it's not just r, but it's going to be the radius of the wheel, or radius of the sphere, or whatever it is. In this case, a cylinder. So let's come down to an example here, pulling a cylinder with a rope. And I've drawn a picture of what that might look like. If you have like a wheel here with an axle, which is the axis of rotation, and you kind of tie some ropes to both sides and with a cord up here, we can pull this cylinder with a tension force, which is acting at that axis of rotation. And so that's what we're doing. Okay, mass, radius, and the tension is given. First thing we're going to do is draw a free body diagram. We want to figure out what is the acceleration of this cylinder. So be in that direction. We want to figure out what is the friction force on it and the minimum coefficient of friction on the wheel. If there was no friction, it's kind of like that bowling ball I'm picturing in my mind with those lanes that are real waxed and slippery. If there's no friction, the thing might not even roll. It would translate. It would just be a ball that's just moving forward without any rolling. And so there is friction here. So the trick for drawing a free body diagram with rolling objects is to draw a really large um, circle. And when we put the forces on this for our free body diagram, draw little forces. So big circle, oops, little forces. And big circle, little forces. Here's the axis of rotation. And this is part A. This is our free body diagram. Okay, pause the video. Think about this cylinder, and it's on the ground, of course. It's on the ground. It's getting pulled with a rope. Try to think of all the forces that are acting on the cylinder, all of them, not just the one causing torque. What are all of them? And then when you're done, we'll continue here on this video. Okay, so with small arrows here, clearly we have a tension force acting on the axis of rotation in that direction, little tension force. And the force I like to draw first, usually on these, is gravitational force on the cylinder itself, which is mg. Now it's on the ground. There is a normal force on this, and you might think, oh, we'll just put a normal force up here. Normal forces and friction forces act at the point of contact. So this cylinder is sitting on the ground. The ground will give it a upward normal force going up there, acting at this point of the wheel or the cylinder. And there is a friction force, which is here, going in this direction, friction force. Why is the friction force pointed in that direction? We've done problems before where friction force is actually in the direction of the acceleration of the object, but yeah, so why is it going that way? Well, we're going to answer that exactly right now. Um, Next thing we're going to do is we are going to write our equations. We want to draw, or we want to write the sum of torque is equal to I alpha. Oh, and I forgot to draw it. So, yeah, this thing has an angular acceleration, and it has acceleration that way. Let's start with our torque equation. Um, Look at the diagram, pause the video, think about our axis of rotation, and try to figure out which forces are putting torque on the cylinder. Remember, torque is R times F. And when you're ready, let's come back and we will talk about it. So first we'll talk about which forces do no are not putting a torque on the cylinder. Because the axis of rotation here, any force at the axis of rotation do zero torque. So mg and ft don't do any torque. Any force that is not perpendicular with r is not doing torque. So Fn, we could draw an r. Now I'm actually going to draw it over here. Um, the distance from the axis of rotation to the normal force is right there, but Fn is perpendicular with r. I'm sorry, it's parallel with r. It's not perpendicular. And so Fn is not doing any torque. And the only one that is doing torque is the friction force. And so we will say r times friction force is equal to the rotational inertia of a cylinder, which is m r squared over 2 times alpha. And so why is friction force pointed in that direction? Well, it's not because of what I'm going to tell you here, but it makes sense. Um, it makes sense because if this thing is going to have an angular acceleration in this direction as it's rolling, it needs to have a torque in that direction. And the only torque that it's getting is from the friction. The friction allows it to have this angular acceleration here. Um, so we can simplify this. We can say FF, because the R cancels here, equals M R over 2 times alpha. Okay, we have numbers. We'll put them in here in just a bit. Let's draw or let's write our sum of forces equals MA. And let's look at the direction of the acceleration. We only want forces that are in that dimension. We don't want any forces that are perpendicular with that direction, with that dimension, I should say. And so the force that's giving us a forward acceleration is Ft. Now, FF opposes that direction. We'll put minus FF equals NA. Now we know Ft, okay? Um, yeah, we know M. We just don't know F. We don't know F, the friction force, and we don't know alpha. And so we have too many unknowns here. And so we have three unknowns. We have two equations, three unknowns, and so we can't solve it unless we use that A is equal to R alpha. Now again, and we've done this before, alpha is equal to A over R, and I should have written that first. A over R. And we'll substitute this, of course. So the only expression with alpha is friction force is equal to M R over 2 times A over R. We can cancel R. The friction force is equal to M A over 2. Now we're going to substitute this. We don't know A, so we can't figure out friction force this way. we're going to write Ft minus ma over 2 equals ma. We will get all our a's to one side. This is ma plus ma over 2. And I'll leave this in like a fraction form. We'll get a common denominator here. That's 2 over 2 ma plus ma over 2. That's 3 ma over 2. And let's rearrange this for a. This is 2 ft over 3m equals a. We can substitute some numbers now. This is 2 times 15 over 3 times 2, which is 6. That's 30 over 6. This is just 5, is the acceleration. Okay, and come back down here. We can figure out the friction force, and this is just 2 times 5 over 2, which is just 5. What is the minimum coefficient of friction, necessary to keep this thing from slipping? Let's do that here. D is friction force is less than or equal to U sub s times Fn. Oh, and I want to ask you, what kind of friction? Think about this. What kind of friction is this? This thing is just rolling. It's not slipping. And what kind of friction is that? It's almost by definition, I think. Well, kinetic friction is by definition slipping. By the way, we've defined it. So yeah, this is a static friction. So the friction force is 5 mu. Okay, it's Fn is mg. Fn is mg. And so what's m? That's 2. That's 20. We'll divide both sides by 20. 5 over 20. Okay, I'll write it. 5 over 20 is less than or equal to mu, which is 0.25. So the minimum, in other words, the minimum must be 0.25. Could be greater, but the minimum is 0.25. And I realized, let's see, we did A. Let's put in here B, and let's put C to label our work. Okay, last one. A cylinder on an incline. It's a disk, mass M, radius R. This is angle theta. And let's draw a free body diagram for this thing. Figure out acceleration and figure out friction force. Okay, and this is without numbers. We just did one with numbers. Okay, this is without numbers. So again, let's draw all of the forces on the cylinder. Remember, big circle, little forces. Let's start with mg this time. There is a contact force. There's two contact forces from the slope here. This one is Fn, just perpendicular with the surface, and then we have again a friction force that is slope. Now, kind of rush that, and I think it's because I'm getting tired, but this thing has angular acceleration as it's rolling. It will be accelerating in this direction, translational acceleration along the slope in that direction there. And so there must be a torque on this thing, and that torque, so I'm having trouble with, is Let's make this a different color. Just friction force. Okay. Now, okay, uh, that's weird. Got rid of my circle. Okay, not to worry. We'll draw another one. Just okay. Then the other one popped back up. Sorry, guys. That happens sometimes. Okay. Um, Now, okay, back in the old days when we did this stuff, we want to get our forces into two dimensions. Because there's an acceleration in this direction, we want to keep that as one of the dimensions here. So FF is good. It's along that dimension. FN is actually good because it's perpendicular. What we want to do is we want to do something with MG, break it up into components. And if I'm going to break stuff up into components, remember, you lose points on quizzes and AP tests for not for messing up your free body diagram. Keep your free body diagram, and we're going to draw this separately. This is it's not your free body diagram, it's some other diagram, but with components. Put friction force here. Now I want two components. I want one along this dimension and one along this dimension. Right? If you take that mg, you can make a, again, I don't want to mess this up, but you can make a force here and you can make a force here. Sine slides. So mg sine theta is that one. This one is mg cosine theta. Excuse me. We can write our torque equation. And again, the torque on this is RFF. The rotational inertia of a cylinder, mr squared over 2 times alpha. You can cancel r. So the friction force is mr over 2 times alpha. We don't know FF, we don't know alpha. Two unknowns, one equation. The sum of forces equals ma. So we'll take a look at this diagram over here. Uh, let's look along the direction, the dimension of acceleration here, or direction, I should say. The force causing this translational acceleration, mg sine theta, points in that direction. One opposing is friction force equals ma. And again, should be doing capitals. And yeah, I should be doing capital MG. Okay. And yeah, Fn and mg cosine um, don't contribute to this acceleration. All right, what do we know here? We know m, we know g. Theta is given. We know theta. We don't know friction and we don't know acceleration. Three unknowns, two equations. We need another equation. A is r alpha. Alpha is A over R. We don't ask for alpha. We're going to substitute it. We can get rid of it. We can erase these. Just pointing that out. Um, Friction force is M R over 2 times A over R. Cancel R. The friction force is M A over 2, which we can substitute over here. This is mg sine theta minus ma over 2 equals ma. Yeah, before we cancel m, I'm going to add ma over 2 to both sides. This is ma over 2 plus ma. Sometimes I put it on this side, sometimes I put it on that side. Let's cancel M. Oh, I should have added those before I canceled M. It doesn't matter. Z sine theta is equal to A over 2 plus A. Get a common denominator, that's A over 2 plus 2A over 2. So this is 3A over 2. We want to solve this for A. This is 2G sine theta over 3, or in other words, 2/3 G sine theta. Then we just want to figure out the friction force. This is M over 2 times A, which is 2G sine theta over 3. One thing cancels out. We'll say the friction force is mg sine theta over 3. These are all acceptable quantities. M is given, g is a constant, theta is given, and 3 is constant. Is the friction force. And that is it.